All right, recording is rolling. Welcome to Friday, April 14th. All right, so I have handed back all the quizzes that you guys have taken so far. All the solutions are posted. So we really only have one quiz left, and that's going to be this rotational dynamics on Tuesday. Okay? Now, after that, we're still going to do FRQs. We still got another practice exam on AP Classroom that I can give you guys. So we're still going to be doing stuff, but the last like main quiz, yeah, just been a few days here. Okay? And then today our main focus is going to be this rotational dynamics pulley system. I did give you guys this page. In fact, the last quiz you guys took. So if you have like 5 or 10 spare minutes at the end of class, then you can start working on that. So you might have it with you. You can follow along. You guys got paper out, like notes. Okay. So the way we're going to do this is we're just going to go through question by question. I'll have you guys write in your notes exactly what you think each answer is, and then I'll show you guys the solution, and then we'll go from there. Okay. And then my plan Monday is to I've got a AP FRQ lined up, and then we'll do that like we normally do it, and I'll give you guys some points for doing that. Okay. Okay. All right. So are we good? All right. All right. So I'm in here, and got this printed out. Follow along. It's all right. If not, you can just read along with me here. All right, we got a double pulley is built by welding together a solid disc of radius R1 and a larger disc radius R2, so the discs are coaxial. Okay? Coaxial, so like they have the same axis right here in the middle. The double pulley is supported on a horizontal axis that passes through the plane of the page. I mean, you could get that all from the picture. They're just explaining that in the paragraph. One string is wound several times around the smaller disc, and a block of mass M1 is hung from the free end of the string to the left. Another string is wound several times around the larger disc, the block mass M2 is on the free end of the disc to the right. Okay. Yeah, I think that whole paragraph you could get just by looking at the picture. That's the implication how they set it up. Okay. Suppose, okay, so the fact that there's like an axle in the middle and they're both spinning around that and they're all welded together, right? You got a string wrapped around here, you got a string wrapped around there. Okay. Two different strings. Okay. Suppose mass 1 is 9 kilograms and radius 2 is 3 times radius 1. Okay, so this radius 2 is 3 times radius 1. Okay. What mass must M2 have in order for the system to remain at rest if the system was released from rest? And explain how you formulated your answer. Okay. So go ahead and write down, might jot down a couple of sentences, maybe possibly back it up with a formula. All right. So who thinks they know the answer? What needs to be the mass? What do you guys got? All right, 3 kilograms. Does everybody else say 3 kilograms? 3 kilograms? Right. Yeah. So there you go. It's 3 kilograms. Okay. So I'm gonna show you their answer, and then in case you didn't get it, then I'll also write down some stuff for you. So we're looking for 3 kilograms. Right? Mass 2 has to be 3 kilograms. And their explanation goes, right, see how close yours is to this. Any work is shown that um, indicates that mass and radius are inversely proportional. This might be a statement of balanced torques. That's what I did, right? Like balancing torques, right? Or some argument based on center mass, or just the equation M1R1 equals M2R2, which I would derive that from torque, but I'll show you guys that here in a minute. Or a statement that mass and radius are inversely proportional. Okay? So I would this. Right? So this mass 1 at radius 1 is trying to make the whole thing turn counterclockwise. There's a torque there. And this mass 2 has a weight. I'm calling it F2, but it's like M2G, right? It's trying to make this whole thing turn back clockwise. Okay? And I want the sum of the torque to be 0 newton meters. Right? So those two torques have to balance. So one torque minus the other torque has to zero up. Okay? So then shuffle this over, and the values of the torques have to be the same. Okay? Now, instead of force, the forces could be the weight of each one. I mean, if it's at rest, that would be the case. Anything in equilibrium. Okay? Now, if it's accelerating, it might be a little bit different. But okay. All right, so looks like this. The gravity field cancels. Right? Now, they did say the proportion of the radial sizes. Right? It said R2 is 3R1. So where R2 is, I'll do 3 times R1. We're solving for M2. And M1, they told you, was 9 kilograms. Right? And so that's the point, that the radial size cancels out whatever it is. Right? You know the proportions of the radius, they just never give you an exact number. Right? Although you can make something up, you say 1 meter if you want. But even if you didn't, divide the 3 down. 3 kilograms equals mass 2. Right, there you go. There's a derivation right there. Okay, so you guys got that? There we go. All right. Next one. For parts B and C, assume that the masses are equal. So M1 equals M2. Okay. The system was released from rest. So question B, which block rises upward once the system is released? And explain your reasoning. So equal masses, which block rises upward? Explain your reasoning. All right, and what do you guys say for that one? How many guys said block 1 rises? Block 1. All right, that's most of you guys, right? Which is good. So, go. Block 1 rises upward. Valid explanation given, such as block 2 exerts more torque and therefore falls, or block 2 falls further than block 1 rises, allowing potential energy to decrease the kinetic energy of the system to increase as the system accelerates. Again, I would gone with the torque explanation, although yeah, if you said something about energy, that would have been would have worked too. Right? I mean, here let's look at the torque explanation first. Right? So, remember we're saying they're the same weight. If they're the same weight, that's like the same force, right? So we got counterclockwise torque, we got clockwise torque, and the clockwise torque is going to be 3 times as much. So you see here calls torque 1 and torque 2. You guys see torque 2 is is equal to 3 times torque 1, right? This is torque 1 right here. So 3 times torque 1. Okay. Torque 2 is 3 times torque 1. Okay. Right. Now, if you had gone with the energy explanation, that would have been an interesting way to go too. Right? Kind of like ball tends to want to roll downhill, water wants to flow downhill. The center of mass of the system would also move downward because of that motion. Right? Like one block's going up, one block's going down, but block it's going down is going more than the block that's going up. So overall, the system moves down, right? Which is how things tend to want to move. Okay? A little bit different way to think of it. Right, part C. Okay, now remember we're still under the assumption that they're the same mass blocks. Which block has a greater magnitude of acceleration after the system is released? Or do both blocks have the same magnitude of acceleration? Explain your reasoning. Ooh, kinematic type question. All right. Let's see, show hands. How many guys said block 1 has greater acceleration? Who said block 2? Okay, so more said block 2. Okay, so take a look here. Block 2 has the greater magnitude of acceleration. Okay? So valid explanation is given such as block 2 has the greater linear motion because it's connected to the larger radius wheel, or block 2 falls faster than block 1 rises. Okay. Allowing potential energy to decrease and kinetic energy to increase as the system accelerates. Okay, so actually I can energy type explanation. Actually, I was thinking more in terms of their first approach myself. Right? So I was thinking of this. Right? You guys know this? So if you have a turntable, like turning, right? And since these are welded together, they all have the same angular motion, don't they? Right? So they all go through the same like turns, right? How many radians that is. Right? They're all turning equally as fast, right? Same like radians per second, whichever way. Right? And it should be accelerating, and the angular acceleration is going to be the same for both. Right? But if you look at any individual point, like a point here, a point here, a point out on the edge, right? Those linear motions are going to be different. Right? And in fact, those linear motions is going to scale up proportional to the radial distance from the center. Right? Like here, if you're at the center, do you have any motion at all? No linear motion at all. You have zero displacement because you're zero radial distance from the center. If you point a radar gun right at the center, it's going to read 0 meters per second because this is also 0, right? And it's not accelerating either, right? If you're a little bit removed from the center, okay, well, now you have a little bit of motion, right? Pointed radar gun right here, you get a little bit of speed. Right? Pointed radar gun right here, it's going to be moving a lot faster, right? Now, they asked a question about acceleration, but you guys see it all goes hand in hand, right? It scales up proportional to the radial size. In fact, if you said that the block on the right, mass 2, accelerates 3 times what mass 1 does, of course, one's going down, one's going up, so direction aside, if you said it's a 3-to-1 ratio in terms of the magnitude of acceleration, that would have been exactly correct, right? Because again, it's all the same angular acceleration for this. Right? Same angular acceleration. 3 times the radius is going to be 3 times linear. Right. Part D. Whoops. Right. Does the gravitational potential energy of the M1, M2 Pulley Earth system? Ooh, okay, so got a lot in that system, right? Each mass, the pulley, and the Earth. The fact that they're throwing the pulley in there makes me think the pulley does have some kind of rotational inertia. Does the gravitational potential energy of the system increase, decrease, or remain constant as the blocks accelerate after the system is released? Explain your reasoning. So go ahead. All right. Let me see. Show of hands. We've got 3 options, right? So we're thinking about potential energy of the system, also include the Earth. Increase, decrease, or remain the same. Show of hands. How many guys said potential energy is going to increase? How many guys said potential energy is going to decrease? How many guys said stays the same? Okay, so no one said increase, which is good. And I've got, looks like an equal split from those last 2, right? Now, there is something that remains constant. What about the energy remains constant? The total mechanical energy, right? If you add together all the types of energy, and I think I can sort of think of 3 categories of energy. Right? What are the 3 categories? Okay, right. So we got gravitational potential energy. I could call that MGH. Right. We got maybe like translational kinetic. I could call that something to do with like 1/2 mv squared. Right. And then each block could have its own kinetic energy. Right. There are other forms. If you think like a spring or something that could be an option, except this case there's no spring, but there is a rotational kinetic energy, right? 1/2 I omega squared. Right? And this I would specifically refer to the that pulley, or that's what I'm thinking. Like, if you treat each block as the 1/2 mv squared, right? And then the pulley itself has some 1/2 I omega squared, right? It's got some mass and it's like rotating. Right? The more massive and the larger radius that pulley, the harder it is to get it to change its motion, right? That's like rotational inertia, right? Right. So if you combine all 3 of these, they have to stay constant, right? So the sum of the energy, so the sum of energy is constant. Right. Now, if the sum of the energy is constant and the system is accelerating, okay, so you release it from rest, release it, and it starts moving, and then it moves faster, faster, faster. Okay. Which of these forms of energy are picking up energy? Increasing. Yeah, the kinetics, right? So each block is getting some kinetic energy. Maybe I should do 2 of these, 1 for each block, right? But each of those is gaining some speed, so it's getting kinetic energy. Right? Now one's going up, one's going down. Does that make a difference? That one's going up, one's going down. Do you have to consider that for kinetic energy? No, correct, right? Because this is this a vector or a scalar? Scalar, right? Momentum was a vector. Kinetic energy is a scalar quantity. So you don't, if you're just focused on kinetic energy, like energy motion, right, direction doesn't matter. Right? And then, of course, the Pulley system also increasing its omega. Right? That's going to make it spin faster too. Right? Guys, is this V and this omega connected? Yeah, right. And it's through R, right? You guys remember V is equal to omega times R, or sometimes you see it the other way, omega equals V over R. Right? Be ready, be comfortable to go back and forth between those. Right? Um, each block will have a different V because it's different, connected to different radial location. But that's not. So guys, if the total energy is constant and the kinetic energy is increasing, what do you know about potential energy?
Be decreasing.
Has to be decreasing. Okay, that's the answer. It has to be decreasing. Right. Alternatively, here, let's go back and look at their model. Right. Okay, so this is like accelerating this way. Right. Now mass one's going up. Hold on, pause for a moment. Right. The Pulley system doesn't move; it stays fixed in place. So the potential energy of the Pulley system that doesn't matter, right? Doesn't change. Mass one is going up, but mass two is going down. And mass two has to move down more than mass one moves up because of how it's located. Right? That provides more torque. Right? So do you guys see that overall the center of mass of this entire system is moving downward? Right? Of the two block Pulley systems moving down. Right? And since potential energy is mgh, and the that height value of that center mass of the of this three object system, you know, if I throw out the Earth, right, is moving down. Okay, is it? And if you include the Earth, right, it's getting closer to the Earth. So right, got that. All right, so let's look at what they went with the answer. All right, that was part B, right? So you have to indicate that potential energy decreases. Right? They were looking for a valid explanation given such as the kinetic energy of the system increases as the system accelerates, so potential energy must decrease. I would add to that, say, of course, energy is conserved, right? So that's the other important detail to make that work, right? Or block two loses more height than block one gains, allowing potential energy to decrease. That would also work, right? Now, maybe you'd also have to consider the masses of these things to really make that click exactly. But yeah, I like more their first. I like this first statement a little bit more, but I would also include that energy overall is conserved. Part A. Right, so this, is the linear momentum of the M1, M2 system conserved during the interval after the system is released? Why or why not? Ooh. The linear momentum conserved. All right. So I guess it's either yes or no, right? So let me see. Show hands. How many guys say yes? Yes, linear momentum is conserved. How many guys say no? Okay. Oh, nice, nice, nice. Okay. So I think almost everybody got that one. Right. So here, let's look at their explanation and then add a little bit to this. Okay. So no, either for stating that there is an unbalanced external force on the system, or in the system they're talking about, just the two blocks themselves, right? Right. So they changed the system. Like earlier questions referred to like four things in the system, right? The pulley, the two blocks, and the earth. This one we're only talking about the two blocks. Right? Right. So there's an unbalanced force on the system. Student does not have to specify which force, but any mention of weight or the force of the axis would be an unbalanced external force, right? Or stating that the two blocks move in opposite directions with unequal speeds. I think I would have said that myself, right? So their momentums cannot cancel to zero, which was the initial momentum, right? Yeah, so if one block's going up, one block's going down, if you do mass times velocity up, mass times velocity down, take the difference. Yeah, the difference is not going to be zero, right? I would have gone with that, something like that. Okay. Now, what if? Okay, you guys covered that so far. Right. Right. So I want to tag on to this a little bit. Right. How could you change the premise so that the answer would have been yes, momentum is conserved? Because they could have changed the premise a little bit so that momentum actually would have been conserved in the system. Right. And how would you do that? Um, okay. Right. Is there any system where the whole momentum would have to be conserved? Gary? Boom. That's what I'm looking for. Yeah, you guys hear Ruben? If you include the Earth. Okay. So if you include the Earth, right? Now that's kind of a weird thing to think about, but guys, as those blocks are overall falling, I mean, one's going up, one's going down, but the net motion of the blocks is downward. So we figured that out already. Right? Is it also pulling up the Earth at the same time? Yeah. Now, how much does the Earth move up? Do you think like maybe like a fraction of an atom, something like that? Okay, so I mean like negligible, but not technically zero, right? Okay. Um, okay, is that? Uh, all right, so how about this? Right, you guys know that the Earth is pulling down on each of those blocks with a force equal to its own weight, right? Right? And those blocks are pulling up on the Earth too, right? Now, which force is overall bigger? The Earth pulling the blocks down or the blocks pulling the Earth up? Which force is bigger? They are the same. I still can't trick you guys. They are the same. That's Newton's third law, isn't it? So equal and opposite forces, right? Opposite forces. Okay. Different masses, different accelerations, different outcomes. Okay. All right. Part F. Block 2 and its string is removed. Block 1 is released with the system at rest at time 0 and allowed to fall distance d, while the double pulley system rotationally accelerates. Right. So let's go back and look at this picture again. Okay. So we're getting rid of block 2, right? Boink, he's gone. Right. You guys got that? The time t for the block to fall the distance d is recorded. The values m1, r1, and r2 are also measured using appropriate equipment. Okay, so maybe like a scale and a ruler meter stick or something. Explain how the measurements of d, the distance fallen, t, the time, mass 1, r1, and r2 can be used to calculate the rotational inertia of the double pulley. Your explanation will primarily consist of descriptive sentences, but will necessarily require you to cite specific equations and model the situation which they are used. Right. So I can think of a couple of ways to do this. Right. Let's look at actually I'll just walk you guys through this because we're getting close to the end of class. So the way I would probably do it is conservation of energy. I would say sum of energy initial equals sum of energy final. Okay. I would say we start off with some M1. Oh no, actually they have time in here. Never mind. Right here, I'll show you what I was thinking, but change my mind on this. Right? G D distance of fall. Right? And that's going to turn into 1/2. Never mind. You could do it this way. Now I'm thinking of it. Okay. M1 B squared plus 1/2 I omega squared where this omega would be V over R, and V would be okay. Okay, now here's where I wish I had more class time to explain this, but let me do my best here. Do V versus T, meters per second, time in seconds. Okay. The instantaneous speed at the end, VF, is always twice the average speed. I think I told you guys this a long time ago. Okay. So VF is 2 times V bar, which is 2 times the distance fallen over the time. That's where the time would come in. So that feeds in right there and right there. Okay, that's the way I would have done it. And then you can solve for this rotational inertia that way. Okay. Now they went with a different way. Okay. They said acceleration can be calculated 1/2 distance is 1/2 at squared, and they went with forces and torques. Okay. Actually, you know what? I think the bell should have rung, but I think they have got bells off for some reason. Oh, there we go. All right. So you guys have a great weekend, and yeah, we'll do more practice on Monday and quiz on Tuesday.